G'day. I decided to get into RV camping, so I'm going to get myself a Scamp Lite, which is just a small travel trailer. And as part of that, I'm going to do some tech projects for that travel trailer. And the first thing I want to do is set up an IoT system to send back information from the trailer about things like location, climate, and other statuses on the trailer. So to do this, I thought I needed some sort of microcontroller and be able to send information over LTE, kind of the same way as I did in our boat monitor. But the device I was using for that, the Picom LTE device, is no longer available. But I found this device from Sixfab, called the Sixfab Pico LTE, and it's basically a Raspberry Pi Pico with a LTE modem all on one board. So that sounded ideal. So I'll just go through a little bit about how I got that working, and then some of the sensors that I want to add to it, and then tie that into my IoT project I did recently. So to get one of these devices, I just went out to the Sixfab site, selected the Sixfab Pico LTE. I also chose to get the antenna for the GPS. Just added that to my cart, and that's the price in the US. So the first thing I had to do once I got it was to install Micropython on the Pico W that's on the board. So this shows you going out to Micropython downloads. I selected the latest download for the Pico W, that's the one with the wireless interface as well, and downloaded it. Once it's downloaded, I could see it in my download folder. So I went out to the board, pressed the boot button, held it down while I plugged in the board, and then it came up as just a normal file type device. Then I could grab that Micropython file that I downloaded, copy it over to the board, and once it is copied, the board basically does a reboot. And you can see here, after it rebooted, I could do a mode, and I could see the actual board's COM port, which told me that Micropython's running satisfactorily on the Raspberry Pi Pico board. So now I wanted to install a Sixfab Python libraries that I can use. So I went out to their site. I've got the link down in the description on GitHub. Got a copy of the GitHub URL, and because I already had Git on my PC, I just created a folder to hold a clone of that repository down in my temp directory. So I just copied that down using git clone. Once that is there, I went out to my projects directory. I made a new folder, and I'm going to call the project folder for this RV IOT Pico. And what I want to do is copy from that cloned repository I just brought down and put in my temp directory. I want to get the Pico _ LTE folder, and that's going to be the libraries that I use in my project. So I just paste it into the project here. The other file I need is I'm going to use HTTP gets. So they have an example of how to do those. So again, I went out to the repository files, got get.py, copied that. Same thing, copied it over to my project directory. So the last thing I had to do before I could test out the LTE was just register the board with Sixfab. So if you sign into Sixfab, you can just sign up for a Sixfab account. Doesn't cost anything. Go in, and in my assets, I went and registered the board that I'm using. I've already done this, so I can't show you again, but basically just go in and type in the serial number from the board. That registers the SIM with Sixfab. The other nice thing is when you register, you get a year's service on that SIM, and 1 gig of data use, which is a ton more than I'm ever going to use with IoT. And you can give that board a name. I called it Pico RV for my board. So once it's registered, let's go on and test out connecting to LTE. Now, next thing I'm going to do, so I fired up Thorny, and I really just need Thorny to copy down the files. So first I set up my environment to use Pico interface, selected the COM port I'm going to use. I use Thorny to copy a copy of my project directory on my PC down to the Pi Pico. You see here it's copying all the files down, and this is about the only thing I use Thorny for. Most of my coding I want to do in VSCode just because I'm used to it. VSCode using MPRemote does not do a great job of handling folders, so I used Thorny for that, but that's the only time I'm going to copy a whole folder of information, this Pico underscore LTE. Now I've swapped over to using VSCode, and then I'm using MPRemote utility or extension to be able to talk to the Raspberry Pi Pico. I'm doing this just because I normally use VSCode and MPRemote. The only problem I have, and the reason I used Thorny, is to be able to copy this whole folder of files. MPRemote doesn't really do that. At least the extension doesn't, so it's easier just to do that over in Thorny, and then I'm not going to touch that folder again, so I can just leave it on the device after that. The other change is now the device is COM11, and you can see in the photo here it's connected up, and you can see a little light there on it to show that the power is on. So let's have a look at the get Pi. I changed this around a little bit from the get Pi that comes from the examples. So instead of using config JSON to get the URL, I'm just hard coding it into the code here. So I'm going to go to this address, which is just a web server I own. Then it has a statement saying it sent a GET request, calls Pico LTE HTTP GET, shows the results of that GET, and then it just waits 5 seconds and also shows the results of that, and will tell me it's a success if the result was a success. So that should be ready to go. So let me just use MPRemote to upload the file out to the Raspberry Pi Pico, and then I'm going to run that. What we should see on the Sixfab device should be a blue light starts flashing. So first it turns on the LTE modem, so we'll see a blue light for that. Once it starts trying to connect to LTE, we'll see a slow flash. So it'll flash and then sort of delay for 2 seconds, then flash again until it's connected, and then we'll see some faster flashes while it's talking to LTE and is connected on there. So let's run that and see what happens. Okay, blue light, so it's powered up the modem. Okay, it's faster blinking once it got the LTE connection. Sent the request, got an OK, and also shows me the response. And for this particular request, I just have OK in the response as well. And so that all succeeded. So there's a real easy way of getting LTE working on a Raspberry Pi Pico. Now I'll show you some of the other things I do before I get into actually coding this up for using in my RV. Now I know I'll be able to connect through LTE. Let's look at some of the IoT data that I want to collect off my RV. So climate, so usually that's just temperature, humidity, air pressure. I'll get vehicle specific information. At the moment I'll start with what the house battery voltage is and the current draw. The location, so just longitude and latitude. And then I can pick up network information as well if I'm connecting through LTE, I can collect the RSSI value, which is the signal strength. So that's what I'll start with. I'll see what I need to do to collect that data. So I want to do some tests. So first, for the Sixfab Pico device, I was wondering how much power it used. So first I just ran the get HTTP script as it was, and it seems to leave the power turned on for the modem after it's transmitted stuff. It used 0.31 watt hours of energy in an hour. Next I ran the same script, but I had a power off command in it, and this time the modem got turned off and it only used 0.15 watt hours of power. Because typically I only transmit the IoT data once an hour, I'll probably go with the second script where I turn off the power after transmitting the data. So I know I want to get GPS information from the device. So first I had to put an antenna on it. This is the first tricky bit, is you need to use a passive antenna. It's better just to buy the antenna when you buy the device. It took me a while to work out that none of my active antennas was going to work. Then for the code, I just copied that from the example of GPS being sent to the server, and it pretty much worked straight away. It took about 30 seconds for it to get a lock when I was sitting outside with the unit. One other thing to notice is the GPS location request also brings back the current date and time. They'll be useful for setting my real-time clock. For getting climate data, I'm going to use a BME 688. This is a web page. I'll put the link down in the description below. But the BME 688, it collects the common stuff like the temperature in centigrade, the current, humidity, and the air pressure. But it also has a gas sensor on it, and this diagram sort of shows you what it's going to do. Basically, it's looking for volatile organic compounds or pollutants, and if it detects some, the more there is, the lower the resistance will be returned by this sensor. And so that's the way I'll track air quality as well, just by tracking the resistance caused by these VOCs. So lower the resistance, the worse air quality there is. Let's look at how I set that up. So this shows the code that I used to test out this sensor. So I used a BME 688 library. I'll include the link to that library in the description below. So I import the BME 680 underscore I2C object, create an instance of that called sensor. It talks via the I2C interface. And then otherwise it just uses the sensor properties of gas, temperature, humidity, and pressure, collects those and writes them out to the display at the moment. But in the end, there'll be IoT data sent back to my IoT server. One interesting thing, when I first started collecting the gas readings, the resistance was very low, and I found out it's because the sensor needs like a 48-hour break-in period. So you see it started off at about in the 500s, but after a while, probably after an hour or so, it got near the 6,000s and sort of flattened out after 24 hours or so to be about 7,300. I think that's kind of its break-in number. So it does take a while to first break in the sensor, but once it's broken in, then after that it only takes a few minutes to warm up and get the same readings each time. Let's test out the gas sensor. So at the moment I've just got it sitting under an empty cup. It's got a reading of about 7291, which doesn't mean much other than that's the current resistance. So resistance gets lower as there's more VOCs around. So I'm going to test this by putting some nail polish inside the cup. So this is the nail polish. So I'll just smear some inside the cup, where you can see it here, and put that over the sensor, and we should see on the next reading the gas readings dropping quite a bit. So I think it's a resistance value, and lower resistance means more volatile organic compounds, VOCs. So it's pretty bad. So you don't want to sit in that cup. So I wanted to work out how to collect information about the current that my RV would be using, or total current that it might be using, and also the voltage, which in most cases is the battery voltage. So I decided to use an INA 219, which is a current sensor, and they usually come in a package like this. It looks like this has a I2C interface, and then has two wires to collect current information, basically measuring the voltage across a voltage shunt. And there's a diagram of what the INA 219 is doing internally. It's a pretty nice device. There's lots of YouTube videos on it, so I won't get into any real depth. One thing to note on the packages that come, like this one here, they usually have a built-in shunt resistor. For me, it turned out to be a naughty resistor. I actually desoldered that because I'm using a shunt that's off the board anyway. And so I set up the whole circuit to basically look like this. So from the Sixfab Pico LTE board, it has I2C interfaces using the QW-I2C interface. And so I plugged that into the INA 219, got it to measure the current across a shunt resistor. So I just used a 50 amp shunt resistor that you would normally use on a 12 volt application. I'll show you a picture of that in the next diagram. And so basically the voltage gets sourced from the RV 12 volt sources, which will either be the RV battery, or if it's on shore power, from a 45 amp shore power converter. Goes through the shunt resistor, which is very low resistance, and then onto the actual Scamp RV, and I'll probably just connect this into the input of the fuse panel in the Scamp to make this all easy. So there's the theory, and this is where I actually tested it. So I connected up the INA 219 to the Sixfab Pico board through the I2C interface. You see here I removed the actual resistor that was on there. I was getting really weird readings for about half a day until I worked out that the resistor was bad for some reason. It just wasn't set up right. I should have been able to parallel this much lower resistance value across it and sort of taken it out of the picture anyway, but it seemed to be I needed to desolder it from the board to make all this work. And then so I use this board to sense the current, which it does by measuring the voltage across the shunt resistor. In this case, I have power going through the shunt resistor, through a dummy load here, a couple of large resistors, and using my bench power supply just to keep a track of things. So for this run here, I was running the bench power supply at 5 volts, or close to 5 volts, which was delivering about 1 amp through this circuit. And so when I run on the Pico board, using the INA 219 library, and I'll show you all this in the software part of this video. It came out and showed me the bus voltage of pretty close to what my power supply was reading, close enough for what I need it to do, and then measured the current as about 1 amp as well, which again is close enough to the ampage that was coming out of my power supply to work for me. So this should be able to be set up. Later on I'll show you how I actually connect it into the RV, but that may be a month or two away yet. I decided I need a real-time clock module as well for this project because I won't always be connecting to the network. I can't always go to a NTP time server and get the latest time for the IoT event times. So I'm using this real-time clock module which communicates through I2C. So let's look at the code to use this. So this is the code I used to test out the real-time clock module. So first thing I had to do is one of the functions of MPRemote is I can sync the time on the Pi Pico to my local time. So let's do that just to get that set up. I copied down this library DS3231. Then in the actual code I imported the library and set up an instance of the DS3231 library by connecting it with the I2C interface. Now the print statements in here while I was testing. First I show what the current date and time is on the real-time clock device. That should be pretty much now anyway, because I've set it already, so it should be keeping a good time. Then I get the local time off the Pico. That should be in sync with the real-time clock module, but just be aware that when the clock module first came it had a different time on it, but I've already set it once. I want to keep times as global metric time. So for my time zone I have to add 4 hours to the number of hours, so that's what I do here from the local Pico time, date and time. Not very clever editing here, but just if the number of hours is more than 23, then I just throw out this warning and don't go any further. I can set the time tomorrow morning instead. If I have a good global metric time, then I make a tuple out of all the values that I need to set the clock. I show the value of that global metric time, and then I use the DS date time with global metric time that I've calculated to set it, and then I print out the global metric time. Let's try running this, and what we should see is the current time on the real-time clock module should be pretty much the same time as what I set it to, because it seems to hold time pretty good, so I don't need to update it really. So let's run this. So first I scan all the I2C addresses. I see 68s out there, so that's good. And like I said, the real-time clock module is showing this date and time, so year, month, day, day of the week, the hour, and I've set it for global metric time, so 18 is really 4 hours ahead of me, so that'd be 14, and that's a 24-hour clock, so 14 would be 2 o'clock, which it is at the moment. Minute 12, second 7. Then I look at my local time, so you see here this is the local time, so it doesn't have the adjustment for global metric time. Here's the global metric time that I calculated by added 4 hours to my local time, and then I set the real-time module to that, and now we see what the value of the real-time clock module is, and it's pretty much the same as what I started with because it's been keeping good time, so it didn't really need to be set. And my thought is in my code is I do connect to the network when I do get I do connect to GPS to get the location, and as part of getting the location it also returns a really accurate date and time as part of that transaction. So if I do one of those GPS location transactions and it's successful, then I'll update the real-time clock with that new best date and time, which should be pretty much the same as what's already in it anyway, but we'll just keep the times very much in sync with the real time, but I won't be dependent on the network at the beginning to have an accurate date and time. Going to start on the software. So here's the plan. I'll show you at the beginning, then I'll do all the coding, then I'll tell you any changes, and then I'll have a look at the code as well for any interesting bits. So I'm thinking of coding this as just a giant event loop on the Pico LTE module. So some of the things I want to make sure of is I don't want to turn on the modem, LTE modem all the time, because it uses a lot more power than with it turned off. So I only be sending that data through LTE once an hour, so I only turn it on while I'm sending data. So in the event loop, I'm thinking maybe just have like a 5-second event loop, and then every time it's a new minute, it'll go out and get vehicle and climate sensor data. So this is from the INA 219 and the BME 688, so things like temperature and humidity, air pressure and things for the climate, and for the vehicle data I'll be getting the current going to the fuse box and the current battery voltage. So I'll get that every minute, and I'll just put it into accumulators. So just store that data. So probably for each of the values, I'll just get a total and the number of an account, and I'll be able to average it later on. So that's what happens every minute, and I don't need LTE for that. So every time the hour changes, it's going to average the accumulated climate data. So using the total, say, temperature over an hour, just divide that by the number of readings I got. That'll give me the average temperature. So I'll save all those values out to a file, a JSON file, for that hour. So that gets saved away. Same thing for the vehicle data. Get the averages, save that out to a separate file of IoT data. And then I'm going to attempt connecting through LTE. So I won't be able to connect to LTE every time, especially if the trailer's moving or the RV's moving or it's in a place that doesn't have LTE connections. So what I want to happen is, if I can't get an LTE connection, is it just carries on. So it'll carry on making another file for climate and vehicle data the next hour, and just keep doing that. And it doesn't matter if we accumulate a lot of them. With the expectation is we'll send them later. So if we do connect to LTE, first of all, we go out and send all the vehicle data. So we'll have at least one file, probably multiple JSON files of vehicle IoT data. Same thing for the climate data. And as we send it, if we send it successfully, we'll delete them. So it'll be kind of a store and forward like I did in the IoT sensor in one of my other projects. So it doesn't rely on always get a connection to be able to send all the IoT data. So if those go through successfully and we're connected through LTE, then we'll attempt to get the GPS location data and send that. So that's a different type of IoT data I send. Again, can send that through LTE. I only do it here because it needs the LTE modem to be up to be able to do that. So I need to have it powered up. And the other thing I'll do is get the RSSI value. So that's the LTE strength. So again, I can only get that if I'm actually connected to LTE. So I'll get that, and then that gets sent as another piece of IoT data. If all that's successful, we'll turn off the LTE modem to save power, and then resume this loop here. And we shouldn't connect to LTE for at least another hour, but we'll be accumulating values every minute. And these values could change, so I'll probably put it in settings whether this is done every minute, every 5 minutes, every 10 seconds, whatever makes sense. And same thing for sending LTE. If I find I'm using too much power, then maybe I reduce that to every 2 hours or 4 hours, or maybe I do it every half hour. Doesn't really matter. But I'll use a setting to set those. And the other thing I'm thinking of doing, I'm not sure whether I'll do this yet, is to set up a microdot web interface. And I'll have a switch on this the box that houses everything to say whether I want the web interface to be turned on or off. And that's because it uses more power to run Wi-Fi, and I won't always have a Wi-Fi connection. But I'm planning in the RV to have my phone connected to Wi-Fi and have that available as a local Wi-Fi connection when it is connected. So in theory, if that's going, then I can run a web interface on the IoT board. And I'll do that. I'll check if I switch on the web interface and it's not running already, I'll connect to the network and start microdot. And if I turn off the switch and we are connected, then I'll turn off microdot and disconnect the network and disable the Wi-Fi power use. So again, go to low power mode for Wi-Fi, or actually turn off anything that's used there. That's the theory. Okay, I'm going to go ahead and code this up, and then I'll show you the end result and any changes I had to make along the way where this didn't pan out the way I thought. Yeah, so I think got all the code mostly going. So some of the things I added in was in main.py, so this gets auto run when microcontroller gets started up. So I put a flasher routine in here and put a big try except routine in here, so it only it'll always try and run main loop when it starts up, and if there's an exception anywhere in the main loop, then it comes out and saves that exception to a file called exception.txt. So as if something happens and I don't get back to it for a few days, I can always look in the exception.txt and see what the exception is that's causing the problems. And then I'm using the flash routine just to indicate that I've got an exception by flashing 100 times. But otherwise, all the code went into the main loop, and I'll just show you the change is to the actual routines in the flow diagram. But this is the main routine now, so there's quite a bit of code in here. Maybe I could modularize it and distribute it amongst other files to make it a bit easier to follow, but this is really only for me, so this will work. So the main routines are do LTE and do Wi-Fi. So now I added in the ability to send data over Wi-Fi if the LTE is failing. And there's really just a catch-all, so if I'm having trouble with LTE, if it ever gets a Wi-Fi connection, I'll use that to send the data as well. I put in some code where it now does a do LTE and a do Wi-Fi when it first starts up, and that's mainly for testing, just to always have those routines run without having to wait for an hour for them to run with this timer routine. Otherwise, we go into the main loop, which we saw in the flow diagram. So just while true, it'll run through this loop. The loop will take whatever the event loop setting is. So I set that at 1 second, so it's going to loop through here every second, and it's going to do things like first it's going to check whether I pushed the user button on the Sixfab board, in which case it'll exit gracefully. So that's one way to exit. Otherwise, the only way it exit is if it gets some sort of exception or I turn the power off. And then it does the sampling routine, so I'll go out and get the client and get the vehicle, whatever the sample seconds setting is. I've set that for 20 seconds, I think. So for things like getting the amperage, that's useful to get lots of samples over an hour to get a good average of what amount of current's being drawn in the vehicle. And then at the end of the send seconds, it's going to send the data up to the IoT system, and that's in here. And you see here it goes through, tries to send the data using LTE. If it fails to do that, then it's going to attempt to do it through Wi-Fi. And let's have a look at the changes in the code in the flow diagram. It'll be easy to follow there. So once I put together all the pieces of the IoT board for the running in the Scamp, you see the LTE, so the Sixfab LTE board here, the GPS antenna here. I put in a UPS, a 5-volt UPS, so if the power gets interrupted, it'll run off these batteries. And it should last about 2 days, I calculate, off the batteries, so it should cover any outage of power on the actual RV. And then the other things it has here is the BME 688 climate sensor with the VOC sensor on it as well, the real-time clock, which uses I2C, and then the INA 219 current sensor. And I did some tests here, so just to see what the power usage is, and kind of the point is I saw about 6 watts per day power usage, and it'd probably be half that without the UPS, but it's worth having the UPS. So let's have a look at the new code. So it gets some of the values out of the settings.json file. So here's an example of the settings I'm using now. And like I said, it now does a do LTE, do Wi-Fi when it starts up. Then it goes into the event loop for whatever the event loop seconds are. So every second it goes through this loop, checks to see whether the button's pressed. If it's pressed, then it exits the main loop. If it's time for the next sample, then it'll accumulate the values for climate and vehicle information. And then if it's ready to send, then it'll average the accumulated data for climate and data, and save those two sets of data to separate IoT data files in the data directory, and then it does the same for the vehicle information, current and voltage, saves that to IoT data. And then it does do LTE, and we'll have a look at that on the next page, what that looks like. And if that's successful, that's the end of it. If it's not successful, then it'll also attempt to send the data through Wi-Fi. So these are the two routines, do LTE and do Wi-Fi. Again, in the settings.json file, it has information for the SSID, the password, and the host name to use. And I'm using a little local network inside my Scamp RV, so I can set this to tie into that local network, and that's a router that then connects to any outside Wi-Fi. Okay, do LTE. So first it turns on the LTE modem. It tries to get GPS data. If it gets GPS data, it saves it, and also will sync the time if it needs to. So if the time on my local board is out of sync by more than about 60 seconds, then it's going to try and sync the time, update the real-time clock and things, so it always keeps the time in sync. And then for any IoT files it finds, and usually at this stage there's three, there's one for GPS data and then the climate and vehicle data, it'll try and send those through LTE. If that's successful, it'll get the RSSI value from the LTE modem, so that's the signal strength basically, and then other information about how long this routine took, how long GPS fixing took, those sort of things. Puts that all into an IoT file and does another send of that IoT data, and that turns off the LTE modem. So that's the end of it if everything's successful. So a total of 4 files are sent every time it gets to a send period, which is once an hour. If something happens in here, if it can't connect to LTE or it doesn't send all the data files that are available, it'll then drop into do Wi-Fi. Same sort of thing, turn on Wi-Fi, try and connect to my local Wi-Fi. If it does, it'll send any remaining IoT files out there, and then turn off the Wi-Fi modem. And we can see an example of this. So this is looking at the IoT data that I've received on my IoT server. So this is an example where you normally see LTE sends 4 files if it connected correctly. In this case, the next hour, it only sent 3 of the 4 files that were available to be sent. So it failed to send 1 file. So it dropped into sending any remaining files via Wi-Fi, and it actually sends 2 files. So one for the IoT data file that it failed to send, and then an IoT data file that it just created. So another 2 files it sends. Okay, here's the finished device. So I connect in the air sensor now through a aviation connector. Here's the original case cover. So the case is an old Radio Shack case. Won't be able to get those anymore. And there's all the pieces inside. I put a connector for the USB power to the UPS. Up the top is a connector for the current sensing. So from there, it's going to go to a current sensor that's going to go in line with the power coming in from the power converter and the battery. Out of all that is the IoT data gets sent up to my IoT server. I'll put a link down in the description about creating this IoT server. But I can do things like see the status on a device. So in this case, RV, so it shows me the vehicle information. I'm not collecting any current or volts at the moment until it gets connected in. The climate, there's the VOC, that tells me about what pollution's like. The location and the IoT data, so things about what the RSSI or the signal strength was, how long GPS took to get a fix, how long the total LTE send took, how long's the device been up, and then I can also do things like chart data. So for the climate, I might be interested in what the air quality looked like for the last 24 hours. And this is kind of a relative measurement, but lower is worse. So up here it's going good. Down here, quality wasn't so good in the morning for some reason. Maybe I was cooking something. And same thing, you can get the data here. So we saw this before. So I might be interested in IoT data for the RV, and that shows me the data sent in the last 4 hours or 6 hours. And so we see for the last 5 of those 6 hours it was sent reliably over LTE. Looks like it failed here, so I won't see the Wi-Fi information for another hour until it tries to send LTE again. I'll send the Wi-Fi information, but I expect to see 4 of the files to end up being sent via Wi-Fi because the LTE failed at this time. That's about it. So I'll wrap it up here. I go collect the Scamp RV next week up in Minnesota, so I'll do some videos on that for anyone who's interested, and then I'll show actually installing this in the RV, getting the battery connected up and things like that, and getting some real data out of it.